Alright students, in this video we're going to compute the gradient of this magnitude vector to a power. Now I have a video on the position vector and um, uh, some properties of it. I would recommend, if you haven't seen that video, you go and watch that one first, then come back to this one. I play around with this notation and I show a nice little result. So I recommend that you check that one out first. Anyhow, just to remind you, um, r without the underline is not a vector, it's a scalar quantity, and it's the magnitude of the vector. R, I call it bold r, or r underscore, but I'll call it bold r. And that is the position vector given here. So if you just give me any coordinates, I just turn that into a vector, and I have the position vector. And then the unit vector version of this bold r, I put a little hat over it, and I just divide by the magnitude. So it can be a little confusing with these underscore r's and then one's not underscored. Just remember that in my notation, the vectors are underlined, scalar quantities are not. Okay, so we are taking the gradient of a scalar quantity here, and it's kind of cool. If you look at this, this looks like the ordinary derivative, right? The n drops down, you subtract 1 from the exponent. Beautiful. Except remember that the gradient yields a vector, so we're actually just going to multiply this by the unit vector. All right, so without further ado, let's start to show this result. Okay, so what I'm going to do is I'm going to take the gradient of Rn. So here's the gradient operator, and here's Rn. So remember, R without the underscore is the magnitude, and it's raised to the nth power. This is really just an exercise in the chain rule. So here's what this would look like. I apply the gradient to this scalar function here, and so that means I take ddx of this function, put it in the first component, ddy of the scalar function in the second component, and ddz of the scalar function in the third component. And then now it's just in each component they'll look exactly the same, so I'll focus on the first component, but it's just, like I said, an exercise in the chain rule. Here's what happens. Chain rule says I drop the n down, I subtract the n minus 1. Oh, now you can start to see what's happening here. So then I get the magnitude here. So that's where the nr to the n minus 1 comes from. We'll focus on that in a moment. Then I take the derivative of this term, the inside function, with respect to x. And so that means, remember, the derivative of the square root of x is 1 over 2 root x. I'll have 1 over 2 root this magnitude, and then the chain rule again means I have to take the derivative of what's inside here with respect to x, and I'll get a 2x. And then similarly for the y component and the z component. They look exactly the same. You can see the symmetry, except I have y's and z's here. Now, you'll notice that in each of these we have a scalar quantity here, and this is n times the magnitude to the n minus 1 power. So I'll be able to factor that out in front of the vector, and the 2's cancel. I apologize if my 2's kind of look like the partials. And anyhow, I have a vector left here. Now remember, this is x in the I component, y in the j component, and z in the k component. And remember that the square root, this is r, the scalar version of r, not the bold r. So really we have x over r, y over r, and z over r here. And that's what I have here. And this is a vector, so I can just simply, the calculus is done. Now I'm just rewriting things. So I have n to the r, n times r to the n minus 1. This is the vector xi, yj, zk. And this is the same scalar quantity, so that's just over r. That's the magnitude of the vector. Another way to write this is bold r over r, but you'll recognize that bold r over r is r hat, the unit vector version. And so I just write that really nicely, and we get this beautiful result. The gradient of the magnitude vector to the nth power looks just like the derivative that you would expect. And this is going to be really nice when we start doing vector calculus in polar coordinates, and this will give us the derivatives, a nice result for derivatives in the radial direction. All right, good luck.